Hello students, I Professor Pote RK welcomes you to online lecture series of structural design 1, that is design of steel structure. So in today's lecture we are going to learn the tension members. So firstly, what is a tension member? Tension member are the linear structural member subjected to the axial tensile force which will elongate the member. In very short and sweet language, tension members are nothing but the member subjected to the axial tensile force. Now, what are the examples of a tension member? The first example is wire rope of a cable. Cable stayed bridges supporting the deck. In the diagram, this red pointer shows you the cable stayed bridge, and this rope is subjected to the tension force. Or the second example is the bottom cord. This bottom cord of the roof truss. This bottom cord of the roof truss is the tension member. Then, as the member is subject to the axial pull, it elongates and does not buckle. Therefore, we need not to classify the type of the section in the case of tension member. At very first, we must know which cross sections are being utilized for the designing the tension member. The first cross section element is solid threaded rods. The second member which we utilize is nothing than the angle section. The third section which we utilize is cables. Then the limiting yield due to the cross section, rupture of critical section, and the block shear failure. Generally, tension member fails due to the three types of failure. First one is yielding of cross section, second one is rupture of critical section, third one is block shear, and these are the three major causes for failure of a tension member. Then the design of a tension member using single angle and double angle section along with the connections by the bolted and welded connection are the contents of our syllabus. So these are the types of cross section for the tension member. A tension member may consist of single roll section or combined sections as built up section. Usually single angle and double angle section with gusset plate are commonly used for the truss members. The rods or the plate may be used for bracing system in a truss or a built up column. The wire ropes and the cables are used in the case of suspension bridges. Here in the diagram, you may observe various sections which are being utilized for the design of tension member. The very first is round pipe or a tube. Second one is welded eye section. Third one is the square tube. Fourth one is the channel section. Fifth one is the single angle section. Sixth one is the double angle section. Then comes the T section. Then there is two channel box section, 4 angle box section, I chan I section with 2 cover plates and 4 PLS box section. So these are the various sections which are being utilized for designing a tension members. Then limiting slenderness ratio for the tension member. Table number 3 of IS 800 2007 page number 20 gives us idea regarding the maximum value of effective slenderness ratio. The first column is serial number, second column is for the members, and the last column is for maximum effective slenderness ratio, that is KL upon R. Now this KL upon R is nothing but the effective length which depends upon the support condition, and R is root radius and it is directly given in our steel table, and we have to take out the minimum one. So the member carrying compressive load from dead load and imposed load, that is live load, it is taken as 180. Hence that is the compression member is having slenderness ratio 180. Then the tension member in which reversible or direct stress occur due to the load other than the wind or the seismic load, that time the maximum effective slenderness ratio is 180. And the next is when the member is subjected to compression force resulting only from combination of earthquake or wind action, that time the maximum slenderness ratio is of 250. The compression flange of a beam against the torsional buckling is 300. Then the members normally acting as a tie in a roof truss or bracing system not considered effective when subjected to the reversible stresses, that time the slenderness ratio is 350. And last one, that is the members which are always in the tension other than the pre-stress members, the maximum slenderness ratio is 400. Then design of tension member, we utilize section number 6 of IS 800 2007 for designing a tension member. Friends, we know that the tension member can fail due to the yielding of cross section, rupture of critical section, and block shear. Hence we need to calculate all the three strength, and after calculating this design strength, we have to check the minimum strength from these three and thereafter design the section from this three strength. So let us begin with the design. The design strength TD of a member shall be greater than the factored tensile acting load on it. That is, TD is the design tensile strength of the member, and TU is factor load which is acting on that member. It is clear that if the section is sufficient to take the load, then and then only it will be able to sustain the structure. The design strength TD of a tension member is least of number 1, design strength due to yielding of cross section denoted by TDG, design strength due to rupture of critical section, that is TDN, design strength due to block shear, that is TDB. Now the first one, that is design strength due to yielding of cross section TDG. It is calculated by the formula TDG is equals to AG into Fy divided by gamma m0. Fy is yielding strength of material which is equals to 250 MPa. Ag is a gross section area of a cross section. Gamma m0 is a partial factor safety for the failure in the tension by yielding, and it is equals to 1.1 calculated from table number 5 IS 800 2007, and it is given on page number 30. This Ag is nothing but the gross area of the cross section, and we calculate it from the steel table. So in this way we have to calculate the design strength due to the yielding of cross section. The next is design strength due to the rupture of critical section, that is TDN. Now as we know that there are different elements for which are being used for the design of tension member. So this rupture of critical sections is calculated for the two members, and which is as given. For the plates and the threaded rods, TDN is equals to 0.9 into Fu into An divided by gamma m1. Here Fu is ultimate tensile strength of the material which is assumed as 410 MPa. Then An is the net area of the cross section after deduction of bolt hole, which is equals to B minus N into DH into T. Here B is the width of the section, minus N means number of hole, DH diameter of hole, and the T is nothing but the thickness of the section. Gamma m1 is a partial safety factor for the ultimate tensile failure by rupture, which is equals to 1.25 calculated from table number 5 page 30 of IS 800 2007. Then second part is to calculate the design strength due to the rupture of critical section for the angle section. Usually we calculate it for the single angle section. So TDN is equals to 0.9 into ANC into Fu divided by gamma m1 plus beta into AGO into Fy divided by gamma m0. ANC is nothing but the net area of the connected leg, and AGO is cross area of the outstanding leg. Fu and Fy are the yielding and ultimate stresses respectively. Here beta is calculated by the formula 1.4 minus 0.076 into W by T into Fu by Fy Bs upon LC, and this is less than Fu up into gamma m0 divided by Fy into gamma m0, but value of beta should be greater than 0.7. Here in the calculation, first of all we have to calculate the beta, where W is outstanding leg width of the section. We will be studying this, how the calculation of the beta, in the next slide. Bs is the the shear leg width. LC is the lengthening connection, that is distance between outermost bolt or equivalent length of a welding in a load direction. Here if you observe the diagram, these are the holes 1, 2, 3 and 4. LC means distance between center of first hole up to the last hole. Then BS varies case to case. In the case of bolted connection, BS is equals to W plus W1 minus T. W1 is the length of unconnected leg plus W1 is the length of W1 is the length distance between the center of the bolt up to the end of the section. And in the case of welded connection, BS is equals to W and T is the thickness of the leg. By substituting T is the thickness of the angle section. By substituting all this value in the formula of beta, we have to calculate this beta and almost note it again that value of beta should be greater than 0.7. The third step of our design is to calculate the design strength due to the block shear, which is determined by TDB. Design strength due to block shear TDB. The failure of the end connection as unit along the center of the bolt hole in the tension and the shear plane is called as block failure or a chain failure. The block shear TDB is a list of the given below. Dear friends, we have to calculate 2 times the block shear, that is TDB1 and TDB2. Here TDB is minimum of TDB1 and TDB2. TDB1 is equals to AVG into Fy upon root 3 gamma m0 plus 0.9 ATN into Fu upon Fy upon gamma m1, and TDB2 is 0.9 AVN into Fu divided by root 3 gamma m1 plus ATG into Fy divided by gamma m0, where AVG and AVN are minimum gross and net area in the shear along the line of transmitted force respectively. ATG and ATN are minimum gross and net area in the tension for the hole to the toe of the angle perpendicular to the line of transmission. Here this is the tension area denoted by the red dotted line. E is the edge distance, P is the pitch distance, and the shear area is on this side. The tension area and the shear area along the direction of the loading. So dear students, these are the design steps for the tension members. In next lecture, we will be studying the numerical on the design of tension member. Till then, keep watching and subscribe the channel. Thank you.